let's get started. Okay, hello everyone. Welcome to week 4. Today will probably be a pretty empty class today just because there's a lot of midterms happening. So if you're watching the recording right now, I hope you did well. But yeah, before we start, make sure you do the attendance, please. We're not quite hitting our 90% target for food next week. So if you forgot to fill it out in maybe the past weeks, please just fill them out now because I would like to be more broke and then you guys have free food. So yeah, if you fill those out, then I can bring food next week. But if not, then I guess I get to keep my money or something. Um, but yeah, if you haven't grabbed one already, feel free to grab one of these benchies up here. I'm going to be talking a lot about 3D printing today. In terms of curriculum, it's in terms of assignments, it's pretty light. But yeah, there's a lot of 3D printer talk today. So anyways, let's just get started. Again, we're going to be doing a lot of 3D printing. But before that, I'm going to talk about the finals. So some of you have been asking me about the finals and kind of what we're going to need to do for that and the timeline. So you may have seen this slide earlier in past weeks, but some of this might make a little bit more sense to you. So basically your final is to create a CAD model from scratch. It can kind of be whatever you want as long as it's school appropriate. Please don't do something that we've already done in class. That's kind of self-explanatory. So don't send me a hair dryer for your final project because that's just something we did already. But you know, the whole point of this assignment is to be as broad as we can. So you can literally make anything you want. The only thing we ask is that it contains 5 design features, and it must be designed with manufacturability in mind. When I mean manufacturability, I mean manufacturability for 3D printing. So that's why I'm going to be talking about 3D printing a lot today, just so you can get an idea of what you might want to keep in mind when you're designing things, right? Because certain manufacturing techniques have different limitations, and being aware of that is very important when you're designing something. You don't want to design something that may look really cool in a model, and then when you go to make it, it's impossible to make because then your part really won't work. So yeah, please design for manufacturability. We're going to be giving you a lot of examples today, so I hope you listen to that because again, when you finish these finals, you'll have the option of getting them 3D printed by me. So if you design your final well, then it'll make my life easier. And then that means I won't hand you a pile of filament that broke as I took it off the print bed. I've done that a couple times and it made me kind of sad, and I kind of felt bad because some people spend a lot of time on their finals and it looks really great in Fusion, but then when they print it, it's really hard to print, and then it's kind of disappointing. So yeah. In terms of timeline, the final will be due 1 week from the last class. So similar to your homeworks, it will be due on the Monday of the class, of the following class. But since there is no following class, it'll just be due on that day at midnight, if that makes sense. So it's a 5-week course, but your final is due on the 6th week, I guess. So yeah, does that make sense to everyone? Okay. And then when I say 5 design features, you can have duplicate design features. So you could have more than one extrude. So I would say one extrude counts as a design feature, or one fillet counts as a design feature. So you've probably if you think about it a little bit, 5 is a really low bar. You could probably whip that out in 5 or 10 minutes, right? But I encourage you to spend a little bit more time on it. Just personally for me, I like seeing really epic finals, and you kind of get a little bit more out of it. So again, Like you've seen this slide before. These are all finals that people have made in this class. A lot of these people had zero design experience before taking this class. So it goes to show that like all of this stuff is possible, even if you like didn't know how to make stuff when you first started here. But yeah, any questions about the final? Okay. Also, if you ever have questions later, you can just like message me and I can answer your questions. But yeah, that's your final project. Feel free to start now or start later. It's totally up to you. But yeah, with that out of the way, I'm going to be doing a lot of rambling. So we have a couple things to do today. We have one assignment and we have a quiz. But don't worry too much because like the quiz is like infinite attempts and stuff like that. So it's nothing crazy. But I just hope you listen because all of this stuff will be really useful when you design your finals in the next week or so. So yeah. Okay. So when people think about manufacturing, especially in like movies and stuff, you typically think of something like subtractive manufacturing, right? You take some amount of material and then you'll cut it away with some kind of tool to get your final product, right? So up here, you see on the left, there's this like square, and this tool comes in and cuts it away and makes this model right there. Um, that's kind of subtractive manufacturing. It's pretty traditional. We've been doing it for a really long time, and because of that, there's many ways of doing it. So here's just a couple examples of subtractive manufacturing. So stuff like drilling and milling, along with turning things on lathes, counts as subtractive because you're cutting things away. And stuff like grinding too. Like if you have an angle grinder and you're grinding away at some kind of plate, that is all subtractive, right? So subtractive is great, but sometimes it can require really expensive machinery. Like mills can get within like the hundreds to million, like hundreds of thousands to like over $1 million for like really, really nice ones. And for me as a student, I don't really have that kind of money. If you do, that's like awesome. But I don't have that kind of money. So typically like stuff like this is reserved for, big machine shops, except for smaller stuff like drilling and like grinding and stuff like that. The other different or the other manufacturing process is additive manufacturing, and that's when you kind of take a material and you deposit it in some way to create your final part. So a lot of you will think about 3D printing when you think about additive manufacturing, but there's also injection molding, which is a more industrial process, but it also counts as additive manufacturing. But the concept is the same, right? You take a material, um, you extrude it out, or you form it in some way to make your final product, right? So we're mainly going to be talking about additive manufacturing, specifically 3D printing today. But keep in mind that all of these processes are available to you when you're designing stuff. Um, but also, depending on your budget, some of these may not be in reach. So yeah, today we're doing all 3D printing just because I think that's the most relevant to us. Obviously, there's a bunch of applications for 3D printing, and the applications are growing all the time. People think of it as like a really good rapid prototyping tool, which it's great for, but it's also starting to see its way into final products, right? So there's some pretty cool car companies making like 3D printed like wishbones and stuff like that for suspension. Um, and it's 3D printed and it's going on the final car. So it's pretty cool. Obviously, that's not the only thing you can do with 3D printing. Um, it's great for aerospace because you can, precisely like specify where you want materials. So you can optimize parts and get those really cool organic looking shapes. Typically, if you do machine something like that traditionally, it can get ludicrously expensive. But with 3D printing, stuff like that gets a lot more affordable. There's also people 3D printing houses with like concrete and stuff like that, which is also pretty cool. And there's people doing like 3D printed meat and stuff like that too. Um, People do like jewelry, and it's also pretty good in the dental field actually. I know a company who does resin printing for what do you call it? Like those retainers, like those clear retainers. You know, it's a highly specialized part because everyone's mouth is different. But then they use 3D printing to 3D print retainers for people. So that's one really good application for 3D printing that's in use today. Obviously, there's a bunch of different types of 3D printing. The more industrial side, you'll see like SLS or SLM 3D printing, and that's basically when you take a powder and you use a laser. That's where the L is, um, to kind of melt the part, and then you add more powder on top and you melt it again, right? So SLS is selective laser sintering. Um, it's pretty cool. It can get pretty expensive, but it is a great process. You can get a lot of strong materials, including metals. Um, Something more available to us students is something called SLA 3D printing. And instead of using a powder, it uses a resin. Typically, these resins are UV curable. So it basically has a display on the bottom that will shine UV light in like very precise geometries. And then can do that over and over again until you have a part. But the the type of 3D printing that is probably most familiar to you is FDM or FFF 3D printing. So we're mainly going to be focusing on that today because that's what your finals are going to be made of. So if you didn't know, FDM or FFF 3D printing basically has a really long uh, like strand of something that we call filament. It's really just like a thin piece of plastic that is hundreds of meters long that feeds through a hot nozzle to get your part, right? So the way I like to simplify it is it's kind of like a fancy hot glue gun on a robot, right? So you know how a hot glue gun works? You take like the stick, you put it in, and then you pull the trigger, and then it extrudes like the glue. Instead of the glue, we have a plastic, and then we have a computer controlling everything, right? So because you're doing it with a computer, you can precisely deposit the material in different places, and you can do that over and over again until you have a fully 3D part. Typically, how it works is you'll get a model. A program will slice the model up into really thin sections, and then the model or the program will calculate a toolpath for the printer to follow. It's generated something called G code, which is like a machine code for the printer to follow. And it'll basically print one layer, it'll go up a little bit, and then it'll print another layer, right? And it'll do that like hundreds of times until you have your part. Does that make sense? Cool. So with that in mind, there's a bunch of settings that goes into these programs to make your part, just because there's so many different things that could change, right? So if you think of like a normal 2D paper printer, you might be able to change the scale and then maybe like the DPI, which is like the dots per inch. But because you're working with a 3D material, there's a lot more that you can change, right? So the first one that's pretty important is called layer height. Basically, differing layer heights can give you differing strength and speed properties. So basically, over here on the left, you can see that the thickness of each layer is really high, right? It's 0.8 millimeters. But as we go farther to the right, they become more and more fine, all the way down to 0.1 in this example. So I don't know if you can see on the projector, but You can kind of see the layer lines if you are on the left side, but as you go farther and farther to the right, they become small enough that it becomes a lot harder to see, right? So depending on your scenario, you might want to choose one or the other. Um, a 0.1 millimeter layer height looks really nice, especially when you're printing fine details. But because of the increased number of layers the printer has to make, it takes a lot more time, right? So if you think about it, like if you print something like the same model at zero point 0.1 millimeters and zero point 0.8 millimeters, the zero point 0.8 millimeter print will be like 8 times faster, right? Because it has like 8 times less layers to reproduce. So depending on what you want, there's usually like a fine balance in the middle where you kind of want to balance like your quality with speed because you don't want to wait forever for your part. Um, I'd say like the vast majority of people use a layer height of 0.2 millimeters, but that really, again, depends on your application. But zero point 0.2 is usually like where people sit at. So again, you can kind of see here uh, as you increase the number, or as you increase the layer height, your speed will go up just because there's less movement for your machine to reproduce the part. But you might like your surface finish might suffer, right? It's not going to be as smooth as 0.1. Um, and then the opposite is true if you decrease the layer height. One small note is that parts with larger layer heights tend to be a little bit stronger than parts with smaller layer heights. And it's just because typically with 3D printers, a lot of the failure comes between each layer, right? So if you break a 3D printed part, depending on the direction it usually breaks along a layer line. So if you have more layers, it gives like more points of failure. So if you want a stronger part, you might want to increase your layer height just to make sure the layers are thicker and they might bond a little bit better. But that's a little nitty gritty kind of thing. The next important thing is perimeters. So if you didn't know, a lot of 3D printed parts are actually hollow on the inside. Setting the number of perimeters can really determine how strong your print can be. So it just kind of tells the printer how many layers or how many loops around the outside and inside of the part that you should go. So you can see here on the left, the number of perimeters is set to 2, so it's a really thin outer layer. But then as you go farther to the right, it gets thicker and thicker, so it typically makes your part stronger. Again, there's the trade-off versus like strength and speed. The more perimeters you add, the more material you're depositing, and just like the more movement your printer needs to do to make your part, right? So it'll take longer to print, and it'll be a little bit more expensive because you're using more material. But if you want a stronger part, that's what you might have to do. The other thing that can affect strength is the infill. Again, like I said earlier, most 3D printed parts are actually hollow. So I'm going to pass these samples around. Uh, some of these are like hopefully those parts are going to be making their way around the classroom. But yeah, you can see that all these prints are hollow on the inside, and it's mostly just to save on print time, but also most of the parts that you make don't need to be completely solid. A lot of the strength will come from the outside, and the inside won't really be doing much. So oftentimes it's good to just like run a lower infill. Typically, infill percentages usually range anywhere from like 10 to 30%. Personally, I run like 25% just because I want my parts to be a little bit stronger. But 15 or like 10 or 15% isn't out of the norm. So yeah, all the prints that I am passing around are at 25% infill. So if you lowered that number, like it'll become like less dense, if that makes sense. So yeah, increasing the infill can increase the strength. Obviously, it adds more material, so it will increase your print times. But for me personally, I would increase the number of perimeters before the amount of infill I use, just because that typically yields a stronger part for the same amount of material. So yeah, does that make sense? Like perimeters and infill, in my opinion, are probably like the two most important settings. So if you don't understand, I'm happy to re-explain. Okay, cool. So the next one we're going to talk about are supports. 3D printing, as much as I wish it could defy the laws of physics, a lot of material or a lot of these prints will be subject to gravity, right? And when you have certain geometries that you want to reproduce, there are certain times where you can't make it without using some sacrificial material, right? So you can see here, this bottom part here has this cylinder that extends outwards, but because there's nothing supporting it on the other side, if you tried to print that, the printer would just run out to the length of the cylinder, but then the material would droop, and then you get a part that doesn't really look like the thing you wanted to make, and then you're going to be sad. So to fix that, we use supports, which is basically the sacrificial material that will print underneath to kind of cradle the part, depending on the geometry. So supports are usable, but if you can design something without supports, that would be even better, right? Because it saves time, it saves material, and you don't have to post-process your part. So like in this scenario, like if you really, really need the specific geometry, then like, yes, you have to use supports. But as a designer, you can try your best to design something that doesn't need supports. Or you can design something to be printed in a certain orientation that can like remove that need as well. So again, supports are something that is kind of like a compromise to me. There's a lot of times where you're going to have to use it, but if you can avoid it, that's great. Okay, so yeah, here's another example. You can see like that H. Honestly, you may not need supports for the H just because you can bridge across. We'll talk about bridging in a little bit. But for that T, if you wanted to print it that way, you would need supports, right? One thing that you could do for all these models is you could have just printed them flat and then you wouldn't need supports at all, right? So again, keeping in mind like which direction your print could be printed in could add or remove the need for supports. So yeah. Oh, is there no bridging section? Or is that later? Oh, it's later. Okay. So with that in mind, we're just going to start doing the assignment for today. So we're going to have you download another software. This is not Fusion 360. We're going to have you download Prusa Slicer. So Prusa Slicer is a slicer. So it's a program that takes your model and it generates a G code for your machine to follow. Obviously, there's a bunch of different slicers out there. Many are very popular. Many are like different copies or forks of the same software. So if you didn't know, Prusa Slicer is based off another slicer that's kind of old called Slick 3R. But then other programs or other slicers have been made based off Prusa slicer, like Bamboo Studio and Orca slicer. So at the end of the day, they all kind of do the same thing. The UI is a little bit different, but they kind of achieve the same thing. We're just going to be using Prusa slicer today just because I think it's nice and intuitive. But these skills can apply to any other slicer. So if you go under resources, I have this link here. If you open it up, it'll allow you to download Prusa Slicer. This is the official website, so there's no virus, at least I hope. But yeah, I'll let you download that. Should take like a minute or two. Yeah. So we're going to be choosing the Mark 4S for this assignment, just to standardize the printer so I can check all the print times. If you use this printer, all the times should be the same. So please use this printer. When you like first open Prusa Slicer, you should be you should be greeted with this like welcome wizard thing. If you kind of go through it a little bit, you'll go down. Okay, wow, well, it's downloading stuff. So if you go under Prusa Research, like this tab right here, it'll basically allow you to select the printer that you want to use. In our case, I'm just going to be standardizing it with this Prusa Mark 4S with the high flow 0.4 millimeter nozzle. So please choose this one, because if you don't choose this one and you slice it, like you'll get a different time and then I'll mark you down for it. So please use this printer. If you accidentally like closed out of this window, to get back into it, you go under this printer tab, and then you go add remove printers, and then add remove printers again. Your thing should probably be a lot smaller than me just because I have a bunch of printer presets already. But yeah, it'll take a second for it to open, but then you can go back into Prusa Research and select the Mark IV, right? Everyone good here? All right. Feel free to just yell at me if you're not there. So you should only have one here. I have like a bajillion because I have a lot of printers. as well. So for filaments, if you haven't chosen them already, go back into that like welcome wizard that was there before, and there should be a filament selection option. So for your filament, just go with generic PTG. Should be like, if you go under vendor and click generic and then click PTG, that just gives you kind of like a random standard profile for a material called PTG. Obviously, I have a bunch of extra ones just because I have a bunch of different ones at home. But for this assignment, we're just going to use generic PTG because that also narrows down the times. Okay. Okay, so if everyone did that right, they should have their selected printer, which is the Mark 4S with the high flow 0.4 millimeter nozzle for under the printer tab. For your filament, if you ever want to change it, you just click on the drop down. I'm doing generic PTG. And then for print settings, we'll change that in a little bit. So this one just kind of gives you a bunch of different profiles, right? So here is kind of where you set your layer height. So there's a couple presets for the different layer heights. There's like a speed and structural one. For this assignment, we're looking for 0.15 millimeter speed for your print setting profile. So it would be right here on this drop down. And again, the 0.15 is the layer height. So each layer will be 0.15 millimeters thick. And it's just set to speed because there's a bunch of settings on like how fast the printer can go. So yeah, use the speed profile to make sure they're all the same. Does that make sense? Okay. So those are just kind of like the first three settings that I would check over when I first start a print. I typically just like lock my layer height at 0.2 just because that's just the one I prefer. For this, again, we're doing 0.15 speed. Over here, you can specify the infill for your parts, so like how dense it is on the inside. For this assignment, we're looking for 20% infill. So you can change that here by going to the drop down and changing it to 20. This is also where you can enable or disable supports. For this, we're going to ask you to turn supports on. For the model we're going to use, you typically don't print it with supports, but I just want you to enable it just so you kind of know where it is. So just set it to everywhere, and you'll kind of see what it does in a little bit. This kind of drop down on the side here isn't the only place where you can change settings. If you go to print settings on this tab up here on like the top left area, it'll give you a little bit more optionality, right? So again, you can set your layer height with the same drop down. It just kind of moved. But then you can change more things like the number of perimeters and like top and bottom layers, but we're not going to mess with that today. Again, for this assignment, you can look here on the slide. We want 3 perimeters. So to change that, you can just change this count from 2 to 3 with the arrow or just typing the number in. If you wanted to, you could also change the infill on the infill tab here. Just leave these like infill pattern and stuff alone for now, just because that can affect the time as well. So I'm not going to mess with that. But if you were ever curious, there's a bunch of different infill patterns for you to choose from. So typically I use grid, which is just like the straight lines that you've seen, but they have like gyroid and like hexagonal infill if you really wanted. So again, that's kind of a preference thing. I like grid because it prints the fastest, and typically like I don't really see any like strength performance benefits from using something else. There is like some slight benefit, but for most of the time it's like not enough to matter. So yeah, I like grid, but your mileage may vary. But yeah, for this, leave it at grid so the time's the same. Okay. Also over here, you can also enable supports over here. So you want it to auto generate supports, and then obviously enable generate support material if you haven't already. But if not, you can just typically just mess with these and maybe change the perimeter, and you're good to go. If you ever wanted like more like settings for you to change as you get like more and more advanced, you can like change this from beginner to normal or expert. And you can see like it gives you a bunch of other options for you to choose from, especially like different speed stuff. We're not going to mess with that today. I'm just going to leave it in beginner mode. But just know that all these settings are available to you. So now that we've set all our parameters, let's find a model to print. So if you didn't grab one, we're going to be printing, or we're going to be slicing a benchy today. So let's just go find it. You can just go on the internet and type in 3D benchy. It's pretty there's like a bunch of them. So let's just find it here. You can go to the 3D benchy website, and I believe you can click on this right here. Nope. I'll just go on Thingiverse. Okay. If you didn't know, Thingiverse is kind of like the repositories I was talking about last week, but Thingiverse is like specifically for 3D printing. Again, there's a bunch of different repositories out there, like printables and like things and stuff like that. Thingiverse is kind of like the OG one, but yeah, others exist too. So for this one, I'm just going to download this one, the 3dbenchy.stl. Don't download the other ones because they just are like partial pieces of the benchy. So we're just going to download the whole thing, which is this first one here with the download button. Yay, we have the benchy. Does that make sense? Last time people like downloaded the steering wheel, so just like download the whole thing, please. But yeah, now that we've downloaded our model, we can insert it. There's a bunch of ways you can insert it. I think there's like file, import, stl/step, but I just prefer Control I. So I'm going to select the file, and then we have our benchy right here. So you can see here, if we zoom in, it's pretty detailed. Like the surfaces are very smooth, but once we slice it, you can you'll be able to see how the slicer works. So yeah, once you get the file in, just slice it, and then you can kind of see how it works. So your printer or your computer will run, and it'll calculate the toolpath, and then you'll be greeted with this rendering right here. So you can see like these colors kind of specify what features are what. Obviously, if you were to print a benchy, you probably wouldn't want to print it with supports, but I'm just showing you how they work. This vertical slider right here allows you to see the different layers, and then this horizontal slider allows you to show exactly what the toolpath is for that layer. So I'm just going to go down to the first layer just to kind of give everyone an idea. So obviously you start with a blank canvas, but as you drag this slider, you can see this arrow represents the nozzle, and each line is a path that the printer is going to follow, right? So this green stuff is for the support material, but then you can see it draws the first layer of the benchy, right? And then if we zoom in and we go up one layer, you can see that it just starts stacking layers on top of each other, right? So if you think about it, it's kind of like 2.5D printing, if that makes sense, because it takes a bunch of 2D like drawings and then stacks them on top of each other. So that's kind of how 3D printing works. You can see as we go up, this kind of reddish orange is the infill. You can kind of see how it's hollow. And then as you go farther and farther up, you get the full model. Uh, if you ever weren't satisfied with like the settings you applied, you can change them anytime you like. But when you do change them, you have to reslice the model, right? Because every time you change a parameter, it's going to have to recalculate the toolpath. So for example, let's say I wanted the infill to be more dense. I could change it to something like 50%, and if I sliced it again, it would recalculate, and then you can see how the infill has gotten more and more dense, right? So yeah, that's basically how slicing works. It's nothing too crazy. Does anyone have any questions? Sweet. Okay, so again, for this assignment, please like have all of these um, settings like applied, because I will be going off of those settings to calculate like your grade basically. So if you do it correctly, you should get the same time or very similar time to me. So for some reason, I think Mac, like the difference is like 1 minute or something. So if your print is like an hour and 18 minutes or an hour like 20 minutes, you're probably fine. But as long as it's in like this general range, like plus minus a minute or so, you should have done it correctly, right? Again, for example, if I like accidentally set the infill too high and I resliced it, the time would change, right? Because I have to deposit more material. So it went from like an hour and 18 minutes or whatever to like an hour 27, right? So that's how I'm going to grade. I'm going to check to see if this time matches, and if it doesn't, then you might lose points. So please apply the correct settings. It should be 100 or 1 hour 18 minutes or something. When you submit this, just take a screenshot of your whole screen, right? So I can kind of see the benchy and then see like the time that is displayed. Don't just send me the time, but like send me the benchy too, because I'd like to see that. But yeah, that's basically this assignment. It's nothing too crazy. Yeah. So going back to perimeters, if you wanted to change the number of perimeters, you just go under print settings, and then this layer and perimeters tab, you can click on it, and then you can change it here. Slicing can be like a super in-depth topic because there's a bunch of different parameters that you can change. I'm just talking about the basic ones now, but if you get into like printer tuning and stuff like that, you can be tuning like your speed, acceleration, and jerk for like optimal quality and speed. It can be pretty fun, especially when you go really fast. So yeah. Okay. So now that everyone kind of has an idea of how 3D printing works in general and how slicers work, I'm going to talk a little bit about 3D printer limitations. So again, like I was saying before, like 3D printers are subject to laws of physics, and we can't just kind of make whatever we want, as much as we'd like that. So there's couple of things to keep in mind when you're designing for 3D printing. One of the most important things to remember is overhangs. So basically, um, like a more extreme angle will be more likely to fail. So if you look at like this model here on the left, you can see that this angle on like the wall is not very aggressive, right? It only slopes out a little bit. That might be like, 30 degrees or something. So it makes the printer, or it gives the printer like enough area to like stack a layer on top of it, right? Um, but as you go like further and further away, then it becomes a lot harder for the printer to reproduce. So typically, like I like to keep most of my designs at like a maximum of 45 degrees. Obviously, sometimes like certain designs will need something else, but the more aggressive you are with these overhangs, the more likely your print is to fail. Modern printers have gotten pretty good at cooling and printing overhangs. So if you have a really well-tuned printer, you can probably go more than 45, right? So like I can go like more than 60 on my printer, but that's like kind of pushing it, right? So depending on your hardware setup on and what machine you're running, you definitely want to keep overhangs in mind. Again, typically, like the standard is like 45 degrees, just because it's a nice like middle between 90 and 0. So you can easily make these with like a chamfer or something like that. So yeah, I recommend 45. If you want to go crazy and go a little bit more, just keep in mind that you might need supports. But yeah. Again, personally, as a designer, you have the power to design supports out of, or you have the power to like remove the dependency of supports, right? If you can design it to not need supports, that's typically better, just because you don't need to pull them off and post-process stuff. And it also saves you a little bit of material too. So yeah, 45 degrees. Let me see. Is there a good example? Okay, so if you look at the benchy that you got earlier in class, you can kind of see the front hull of the benchy is an overhang, right? And depending on which benchy you got, like my printer may have had like worse or better cooling. So if you can kind of see like some pretty bad defects on the front of the hull, it's typically because um, it didn't have enough cooling, right? So one of the reasons why I print benchies is because it's kind of like a mini torture test for the printer. So if you can print a good benchy, then you can typically print like any other model pretty well. So like this front hull is an example of an overhang. So if like the front is really clean, then that means I tuned it well. And if it's not clean, then that means I didn't tune it well. So yeah, that's a good example of overhangs. Another example of overhangs is kind of holes. You may not have like thought about this originally, at least I didn't, but if you think about a hole, the top of a hole, like the angle at which you'd have to print that becomes progressively like higher and higher, right? Like if you drew like a line tangent to the circle and you kind of dragged it up to the top of a circle is like completely flat, right? It's 90 degrees from, or it's like completely parallel to the build surface. So that's like a 90-degree overhang or a bridge, right? And then as you go farther and farther away, it might be like 60 degrees, 70 degrees, until like you meet the sides, which is just 45 or yeah, 90 degrees, or I guess zero. Um, so you can kind of see here on this model, like the top of the hole is drooping a little bit. And it's because the top of the hole is an overhang. So a good example, if you look at the front of the hull, there's these two little, like, I don't know, anchor holes where like the anchor would run through. So if you don't have adequate cooling on your 3D printer, those holes can droop, right? Again, depending on the benchy you got from me, those holes may look more or less round, but that's just something to keep in mind, right? This hole can droop. So the way you can combat this is you can design those overhangs out, right? So over here in the middle, you can see it's just a normal hole. But if we made a slight change to the hole and kind of made it like this teardrop shape, the top of the hole becomes just a 45-degree overhang, right? So you don't introduce any extreme overhangs, so the print won't droop. So depending on like your model, this might be something to keep in mind. It's a nice thing to have in your back pocket. This teardrop shape is really useful. I use it a lot. But yeah, a lot of these are just dependent on the scenario. If you really, really need that really round hole, then you can use supports, right? But if you can avoid it, you can add something like a teardrop, make your life a little bit easier. Bridging is also very important when it comes to 3D printing. Please don't like give me a really long bridge for your final. I've said don't do bridges or don't make really long bridges, and then someone sent me a Golden Gate bridge for the final. So please don't do that because that just does goes like exactly like against what I'm teaching you now. So a bridge is basically like when the 3D printer has to extrude filament between two different places, right? There's nothing in between it, and if the bridge is really long, just the gravity from the material having mass will make the part sag, right? So if the bridge is really short, you may not see much, just because the bridge isn't too far, it doesn't sag too much. But as you have a longer and longer bridge, that problem can get worse and worse. So again, if you look at your benchy, if you look at like the top of like the little cabin, there's this nice straight section on the top, and that's an example of a bridge, right? In this case, it's a pretty short bridge, so it can kind of print like okay without drooping too much. But if, for example, like this was maybe 2 or 3 times bigger, that bridge could become a bigger problem, right? Obviously, again, to support a bridge, you can add supports, but then you'd have to remove it later. So if you can design something to not need a really long bridge, then that's typically good practice, right? Again, these are all kind of like model dependent, but because you're the designer, you can like make these not a problem, if that makes sense. So yeah, that's bridging. Please don't send me a Golden Gate Bridge or like the Bay Bridge or something else. Like, please don't do that. If you do that, like design it to be 3D printable. So yeah, that's bridging. The next thing, I know I'm yapping a lot, but thermal expansion can play a key depending on what parts you're designing. A lot of the times, you know, you're going to be 3D printing something that will interface with something else. And 3D printers aren't like exactly precise, right? There's a lot of stuff that goes into 3D printing something. And when you print something, like you heat up the material, and then when it cools, it will contract, right? So sometimes that'll mean your model isn't exactly the right size that you set it to in like Fusion or whatever design software you're using. So you might have to compensate for that. So when you add a little bit of leeway, we call that tolerance. So if you need two things to fit together, you might make one part a little bit bigger and you might make one part a little bit smaller, just so they fit well together. So tolerancing can play a big key in, you know, different parts like interfacing with each other. So keep that in mind. The other thing when it comes to thermal expansion is this kind of is more on like a printer level thing. But if your printer isn't tuned very well, or you have bad bed adhesion, you can kind of experience warpage. So you can see here, like this design was supposed to be like kind of like a rectangular prism, but you can see in the front that corner is lifted, right? And it's because there's like a really sharp edge, and then as the material cools down, it will curl up, and then it'll like pull itself off the build plate, right? So that's not really a good thing. Sometimes it can be prevented with like good bed adhesion on your printer. But as a designer, you can kind of maybe reduce the chance of something warping by like rounding corners, right? So the really sharp edges have a tendency to curl more. So if you add like fillets and stuff like that, you know, it doesn't cost you anything because you're just adding a fillet, and then it'll print nicer, at least a lot of the time. Sometimes things can warp when they're really large and really long too. So if you have a really long part printed in like ABS or something, the tendency to warp is a little bit higher. But again, that's kind of like geometry like specific. So if you can design something that's a little bit smaller, that might help. But yeah. The other thing to keep in mind is elephant's foot is a thing when it comes to 3D printing. And basically, again, 3D printers aren't like extremely precise. They're pretty precise, but sometimes the first layer of a print can be squished a little bit more than others, right? So the first few layers might be a little bit squished, and when that happens, the extra material you extrude out will be like pushed outwards beyond the original geometry you wanted, right? So if you look at like the photo in this circle, you can kind of see like in this example, we wanted the whole wall to be straight, but because the first few layers are squished, there's excess material on the outside, right? And we don't like that, so we call that elephant's foot. So like obviously you could combat that by having a well-tuned printer, but you can also kind of reduce the chance of this happening by adding chamfers, right? So if you chamfer the bottom like at a 45-degree angle. Again, it's a 45-degree overhang, so the printer won't have a problem reproducing it. But then any amount of squish could still be like beneath like the wall that you want it to be at, if that makes sense. So like if you drew like an imaginary line from where my mouse is to like over here, even if it squished out a little bit, it would still be like behind the main geometry that you're after. So again, depending if you want things to interface, if you have a part that's like elephant's footed out and you try to put it into something, the tolerance may not work out. So just something to keep in mind. Typical tolerances for 3D printers, I usually say is about zero point 0.2 to zero point 0.4 millimeters. So if you wanted something to be like 20 millimeters wide, there's a chance that it might be like 19.8 millimeters, or it could be like 20.2, right? So again, it's not exact, so that's why you might need to add or subtract a little bit of material in your design for the printer to print it the way you want. So here's a good example. This was a final from a couple semesters ago. Someone designed this Lego-like figure, and they had, you know, the torso and then the legs, right? So we printed them out, and then when we tried to put it together, they didn't account for the thermal expansion, and the torso didn't go on the legs right? So you see there's that gap there. Obviously, that's not ideal in this scenario, but, you know, they could have fixed it by, you know, maybe making those pegs a little bit smaller, and then that would have allowed the parts to fit properly. So, yeah, that's a good example. If that makes sense to everyone. But yeah. The last thing, your homework is to do a quiz, and it's just kind of all about all the things I've been rambling about today. Feel free to take it now, but you know, it's kind of like an infinite attempt quiz, so it's not like super scary or anything. It's mostly just for your knowledge. I hope you learn from this. Um, yeah, I'll let you all do that now, or you feel free to leave. That's basically all we have today. Today's pretty short. Um, so yeah, please fill out the attendance forms if you haven't already. I'm gonna stick around for a little bit if anyone needs help. But yeah, I will see you next week. Next week we're gonna be doing a 3D printer demo. So I will be bringing a printer to class. If you want to see that, please come. If you have a midterm or something, then don't sweat it. I understand. But yeah, that'll be here next week. So that's something to look forward to.